Okay, now it's time. So I'd like to start the seminar. So thank you for coming today to AI Security Privacy Team seminar. Please allow me to introduce today's speaker, Joshua Butke from Ruhr University. He's a PhD student majoring in bioinformatics at Ruhr University and will graduate the doctoral course this spring. He is currently working on computational pathology using machine learning techniques. And today he's gonna talk about multiple instance learning in label-free computational pathology. So Joshua, if you are ready, could you start your talk?
Yeah, of course. So thank you very much for the invitation. I hope you can see the screen well and hear me well. So as I was already introduced, I'm Joshua from the Ruhr University Bochum in Germany, and more specifically from the Center for Protein Diagnostics, which is an institute, a research institute that's also based in Bochum and closely associated to the Ruhr University. And you've already heard the topic of today's talk, which is multiple instance learning in label-free computational pathology. And not to confuse you directly, so label-free in this case is not related to the notion of labels in ML or AI applications. So it's not the training label or something, but label-free rather means that we work staining-free, which is particularly important in pathology. But we will get to that in a bit. But this is also important because of the institute that I work at. Because at PRODI, we try to discover novel biomarkers for the early detection and characterization of diseases such as cancer or diseases that are neurodegenerative, such as Alzheimer and Parkinson's disease. But today, we will be based in pathology and computation pathology. So we will be dealing with cancer for the rest of this talk. So to get started, as an introduction to pathology in general, pathology is the medical discipline of basically analyzing patient specimens for the analysis of disease or for the characterization of disease. And a pathologist is a trained medical expert that is specifically suited to analyze, for example, tissue in the case of histopathology here in picture A on the left, or cells. So in cytopathology in B on the right. And this workflow is most often based on extracting some sort of specimen, a sample from, for example, a biopsy or a surgery specimen, and then staining it. And that is the part of labeling that I've just mentioned. And by staining it with a chemical stain, for example, the hematoxylin and eosine stain, which gives this reddish and pink stain around the cytoplasm and the nuclei, you can then better visualize the morphology of the cells and of the tissues. And the pathologist is then able to draw conclusions to the state of a particular disease, for example, cancer, as is often done. And this classic workflow has remained the same for now more than a century. It's now, I think, 150 years that the hematoxylin and eosine stain was discovered, and it is still used in the same composition today. And the vast majority of tasks will be based in histopathology, so the analysis of tissue here on the left. And only some applications are found in cytopathology, the analysis of singular cells, for example. These can be found in urine, for example, when cells are exfoliated, so they are shed from the lining, for example, of the bladder into urine, and they are then excreted with urine. They can be collected, and then you can analyze these independent cells. And now, with the recent decade, there has been a change in the field, which is we have now increasing digitization efforts in the field of pathology that gives the rise to digital pathology. So we can now, instead of observing these slides with a light microscope, we can now observe these slides by scanning them in a whole slide scanner, for example, this Leica Aperio, and that digitizes this slide into a whole slide image, which is a pyramidal image, continuously zoomable, of a very, very large size. And that now enables telepathology. So a pathologist can now send around the slide around the world, get a second opinion, annotate them digitally, save them in the database, and so on. So working with digital slides is nothing else than digital pathology. And the field of radiomics or of radiology has undergone this change a vast amount of time previously. So for example, an MRI scan or a CT scan was always based on being processed by computers. So they are always working with computers. But in pathology, this is now a really, really novel development because previously we just had the slides, observed them under the microscope, and then discarded them basically, or put them into an archive. And now with the access to these digitized images, we can work with computers on them and mainly enable AI or ML methods, which I will get to in a bit, which is then computational pathology. But that is not the only case that is possible. As I've said, at Prodi, we try to do label-free whole slide imaging, which means we do not only do virtual microscopy, but we try to analyze the images with a specific type of physical-based imaging method, for example, IR-based imaging, infrared-based image acquisition, or quantum cascade laser-based image acquisition, which is basically vibrational spectroscopy that excites molecules in our sample and then records this excitation to form a so-called spectrum. And the workflow was often as shown here on the left. So we had a tissue sample, and this is now a native tissue sample. It is not stained. So this is freshly extracted from a surgery or a biopsy. And then we acquire a two-dimensional spatial image of pixel values, but instead of the normal red, green, and blue values that you might find as a vector behind each pixel, we instead now have a full spectrum. So a vector in depth of size, let's say 500 data points. And this spectrum is now characteristic for the biochemical composition of the cell, of the tissue at that singular point in time. So it integrates information about the genome, the metabolome, and so on. And then what we often did was we used unsupervised learning, for example, k-means or hierarchical cluster analysis to get some index color image, just basically separating the spectra by similarity. And then with subsequent staining, for example, the H&E stain, as I've mentioned, or an immunohistochemical stain to stain for specific antibodies in the tissue, we could get an expert annotation and build up an annotated index color image. So basically a spectral database with classes belonging to, for example, this is carcinoma, this is connective tissue, this is muscle, and so on. And then with this big database, we did what you normally do. We performed supervised learning, for example, with a simple model such as a random forest, to perform what is called semantic segmentation, to assign each pixel in an image a specific class. So we get a disease-specific index color image. So for example, here in the case of colon carcinoma, so a cancer of the colon or the colorectal system, we then get, for example, pink pixels for the regions of cancer, white pixels for the regions of connective tissue, and so on. And this is basically classic supervised learning, and we have done that for a long time. And on the other hand, we also did not only infrared-based image acquisition, but also Raman-based image acquisition, which is CAS or SS, that's based on a natural occurring scattering effect, which also gives us spatially resolved images, again with a spectral vector in depth. And here we again did classic supervised learning, but in this case for multi-class classification or object detection, for example, to find the deciding cancer cells, so low-grade cancer cells, high-grade cancer cells, and distinguish them from, for example, squamous cells or red blood cells or white blood cells that are not informative for the patient status at this point. And why is it important to work natively or label-free? Well, we can use that to enhance basic pathology by, for example, using laser capture microdissection, in which we then can specifically cut out regions of the tissue and use them for subsequent analysis, for example, analysis of the genome or the metabolome, to better find biomarkers or even novel biomarkers to either characterize diseases earlier or to maybe have a new novel therapeutic approach to some disease. However, both of those approaches, so normal pathology and also our label-free approach, are based on, after all, on the manual pathologist inspection. So we always need the ground truth. And all of these images are extremely large. So we produce images of several gigapixels. And now computational pathology is nothing else than the machine learning-based or AI-based analysis of those patient specimens, most likely automated. But here, of course, we have arising problems and also maybe solutions. So as always, it's about the data. So we have a lack of large annotated data sets. So there's almost no open source data sets, and we have to work closely with clinics and clinicians to acquire those data sets, which are then often highly masked or anonymized to work on those, and have often very low number of cases. We have large amounts of variances we need to encompass. So for example, different staining protocols in the clinics, different workflows in clinical practice. And to just visualize how hard the task is. So here on the left, for example, we have a sample of a prostate biopsy, which is 2 thin needle biopsies. And this is an extremely large image. You can see the sizes here on the margins of the image. And if we zoom in further and further and further. At the lowest level, we can find these tumor glands here on the right. And these tumor glands are not even 300 pixels in diameter. And only 6 of these glands are present in the whole slide. So along both of these biopsies, we only find 6 of those. And now finding this is, of course, like finding a needle in a haystack. It might be possible for a pathologist because he's trained in that area. He can easily find what is missing or what he's looking for. But it's much harder for an automated system. And it's even harder because we do not have the needed annotations. So it's impossible to get pathologists to work for you to do all these annotations, these manual needed annotations in that much detail that we could easily apply some AI system in a fully supervised setting. So of course, the question then was, is machine learning at its limits? And for the longest time it was, because there was no real computational pathology application available in the last 5 years. And only now we are picking up steam or picking up speed in developing those as we enter weekly supervised learning. And now we would like, of course, to have this strong supervised case here in the middle, where for each data point, for example, each pixel in an image, we would have some label to assign it to a class. For example, in semantic segmentation, a class of tissue, or just a patient label in the form of benign or malignant. But we do not have those annotations. Instead, we work in the realm of weak supervision now. So, for example, we could have some form of incomplete supervision here on the right, that we know, okay, some friendly pathologists annotated a subset of data sets for us. However, the vast majority of our data is still completely unlabeled, and we do not have any information about those points. Or we could have inaccurate supervision here at the bottom, where we give our data to some cohort of medical students, and they give us a full labeling because they have the time and can put in the effort for us. However, we will not know if these labels are really correct. So these are inaccurate labels. And the most important case, which we will deal with today, is the inexact supervision, which forms the basis of multiple instance learning, where we have some sort of annotation, but this annotation is coarse-grained. It's only high-level information. For example, the patient status, so the patient is malignant or benign, healthy, non-healthy, but we do not have any information about the elements in our bag, in our data set. So no information about the pixels or about regions in the tissue. And this is what we will deal with in the following. And analyzing these gigapixel whole slide images poses basically 2 problems, which are called or often simplified to the what and the where problem. And of course, a CNN, so a convolutional neural network, could in theory solve both problems simultaneously. However, as these images are so large, this is a computationally infeasible approach. We cannot really put these large images into a single CNN. So we cannot work on the approach of having one image and one singular label. That's not possible. It's just not feasible. Instead, we can try to solve the what problem by assuming that the signal is fully recognizable at the low level, for example, at the level of patches. So we tessellate our image in some sort and could then put this into some CNN. It will solve the what problem. And however, we could also assume that the full annotation is unfeasible even on the level of patches, because no one will label thousands and thousands of patches per sample for us. And instead, the image label could have some patch level representation that is unknown to humans, but this would simplify and solve the where problem. So now, if we tessellate our single image into these singular tiles, so we now have x is equal to the set x1 to xk, all of our single image tiles, however, only still with the large coarse-grained patient label annotation 0 or 1 in the simple binary setting. And this then gives rise to the assumption or the formulation of the basic multiple instance learning principle, in which case our individual labels now y1 to yk for all of these tiny tiles, these are all unknown. However, we can make assumptions if we say, okay, the instances where yk is equal to 1, these are our key instances. We want to find those because if these are present, they formulate a so-called positive bag. A bag can only be positive, as you can see here, with the assumptions about the patient level label, if there is some sort of positive key instance, some positive sub-instance of the individual labels. Otherwise, if we sum up all of these sub-labels and there's no positive instance, then the whole bag is negative, and we can set the patient level label 0. So in the most basic case, this could be reformulated as the maximum operation, for example. So the max of all of our sub-individual labels would give us the patient level label. However, training with the max operation is not really feasible. It's not trainable or just trainable on the instance level, but not in a more common deep learning setting or even a CNN-based setting, as that would lead to vanishing gradients that we do not want. So what do we need in practice now really to solve this what and where problem in the the concept of multiple instance learning. And that is often the so-called pooling operator. So to formulate in a machine learning sense the problem of multiple instance learning, we need some permutation variant model theta X. So the patches are permutation variant in the sense that there's no spatial relationship between them anymore, which is extremely problematic if you think about it for tissue, of course. For cells, not so much, but for tissue, if we tessellate our image and tile out all of these tiny patches, we now have those patches, but they have no relationship to one another anymore. And this will become a problem, as we will see in a few slides. So, however, still for the beginning, we would need some transformation f of x1 to f of xn of all of our individual instances to break them down. For example, some embedding. Then we need some permutation variant function, which is the pooling, sigma, for example, a summation, a max, a mean, a noisy OR. So something that can integrate the information about all of our instances into one bag combined representation. And lastly, we have the transformation G, which is the transformation of our combined instances or the combined bag representation into some classification. And to do that, there currently there were two popular approaches, which were embedding-based or instance-based. And in the embedding-based setting, we had our instances, so these gray squares. And after the transformation F, we would get our embedding. Then we perform the pooling to get here in blue the combined bag representation, and then perform classifier step G, the classifier function G, to get our score, maybe the probability, to get the patient level label, and then we can train. And in the instance-based approach, we would have the same transformation F. However, instead of the pooling first, we first do an instance level classification to get our scores here in red. So these are now all instance-based scores, for example, based on the max operation. And only then we perform the pooling and integrate this information into one combined classification score. However, both approaches had huge issues. So, of course, the embedding-based approach, as you can see, lacks full interpretability. So, if we get some decision here after G, we can never know what instance contributed to the decision. So we will never find out anything about our system. And the instance-based approach basically was impossible to train for the longest amount of time because it propagates error, of course, and has vanishing gradients as it's instance-based. And common to both is that pooling functions that are presented here are not trainable. So they stay as naive as they are in the beginning. They are just these pure mathematical operations, and we do not get along with those. So Ilse et al. In 2018 at the ICML published attention-based deep multiple instance learning, and they leveraged the attention principle, which we will see now, into the realm of multiple instance learning, which was revolutionizing for the field. And now all applications in computational pathology that somehow work with this multiple instance assumption, they are all based on this paper, and they are all based on the attention principle. So attention, of course, I guess you're all familiar with that. So from the attention is all you need paper, or even previously. So we have basically the attention mechanism is an integral part of sequence modeling now, allowing us to capture dependencies without regard to their distance. So in the sentence, she's eating a green apple, humans as well as natural language processing systems can relate eating and apple with a high attention to one another. The words eating and green do not have such a high attention. And now it's the same in vision transformers or the human visual cortex for images. So this is a dog, and of course we, as well as computer vision systems, can easily see, okay, here's one pointy ear, there's another one, a dog-like snout and ear. This will be a dog, and we can correctly classify it as is. However, the pullover or the scarf do not give us any relevant information on deciding that this is a dog correctly, right? So if I gave you this image here on the right, neither we as humans nor some computer analysis system, an ML algorithm, would be correctly able to identify this as a dog. And in particular, transformers are now the most popular approach to use attention, or particular self-attention, first stemming from, as I said, natural language processing, and now also being used in computer vision. And they basically use self-attention to relate different positions of a single sequence to compute some sort of representation. So here attention can be described as a mapping of the query Q and a set of key value pairs. So here's the key and here's the value to some output, which is basically computed as the weighted sum of the values. And they applied this as multi-head attention, which is basically many attention layers in parallel, which was really a big effort and hard to solve technically. but revolutionizing for the field. And basically now transformers have, for the most part, even overtaken RESTnets and CNNs in the application, and are very interesting for the field as a whole. However, what Ilse et al. Did for the multiple instance assumption is they broke it down to some form of basically weighted instance averaging. So instead now of just performing the embedding-based approach, we perform in parallel as a second step. We have another neural network parameterized by the weights W and V, for example, but you could also have many more layers. But it could also be just a 2-layer neural network to in parallel compute attention scores for all of these embeddings. And then these attention scores are multiplied with all of our embeddings, HK in this case, for all of the embeddings in a bag. So due to the softmax function, this is a bag size invariant function, which means no matter how large our bag is, all of the attention rates or attention scores will sum up to 1. And with that, we will get one full bag representation at the end and can then classify on that. So that means now with the attention mechanism as the pooling operator, we have now a trainable pooling operator. It's just a neural network. And the attention rates that we get, so A1 to AK per bag, these can now be interpreted as they give a score to each of our instances that we can find in bags. So we can now say, okay, this is our region of interest. We know where to look at positive bags, for example, because this instance or this cell or this region of the image was attributed with a high attention. So now with that, the embedding-based approach becomes interpretable and also fully trainable from end to end, which was really, really a big step, I think. And to show you for what I've applied this principle with a few modifications in the past, this is a publication which was done at Prodi by me and colleagues, which is end-to-end multiple instance learning for the whole cytopathology of urothelial carcinoma. So we are now dealing with cytopathology again. As I've said, this is the more or the better suited type of problem for multiple instance learning, because in cytopathology we are working on the level of cells. So these cells do not have any spatial relationship to one another anyway. So we can discard their spatial relationship, and there's no dependency. But this dependency would be present in tissue. So we are quite glad to work on cytopathology as a first step, because that is much easier and easier to circumvent the problems. And why do we want cytopathology for urothelial carcinoma? So urothelial carcinoma is cancer that arises in the bladder. So here you can see a dissection of the bladder, and cancer starts in the bladder lining, the epithelium, and then basically increases in size and malignancy, first growing into the bladder, and then also growing into the fatty connective tissue and also the muscle until it invades other organs or metastasizes. So it's really not a pretty cancer, and it's analyzed traditionally by cystoscopy, so by an endoscopy of the bladder. This is quite painful for the patient, as you can see, so it's not really a much liked approach. And as bladder cancer is one of the costliest cancer that has a very high rate of recurrence, you need to test for bladder cancer again and again and again, making it very, very expensive. So we would like to have an alternative test based on cytopathology. So not cystoscopy, but cytopathology now, if we are based on the cells. So here we have now urine, which is just discharged easily and pain-free from a patient. And we basically look at the cells present in urine. So this is urine cytopathology. And we had a collection of those patient whole slide images, all extremely large, and just did a simple extraction algorithm to construct bags of extracted patches for each patient, where each bag contained basically roughly cell-like objects. We also had artifacts included, but all of these were roughly cellular or circular objects that confirmed to some size in area. And then we could perform our multiple instance learning. We had some transformation F, in our case a CNN feature extractor, to compute our feature embeddings. In parallel, we have the attention module giving us the attention scores, as I've just explained, and multiplied with the embeddings, we get our combined back representation, on which we then do transformation G, the NLP classifier, to give us a patient score classification, in our case 0 for benign urocystitis, which is just an inflammation of the bladder, or 1, which is positive, to say, okay, this patient does have urothelial cancer. We found urothelial cancerous cells among all of those cells. And now you might have heard or thought about that multiple instance learning is a really naive assumption. So in the binary setting, if we only get one singular positive instance, the methodology assumes that the whole bag is positive. And that is really a big problem because, of course, in this setting now, we will get a lot of false positives because even a single false positive assumed instance already would lead to an assumed false positive bag. So we included a second step to alleviate this problem, which was based on hard negative mining. And we used hard negative mining in the form of performing, after one training step, performing inference on the training dataset to obtain all of our hard negative instances from the false positive and only from the false positive bags. That means we select these instances in false positively classified bags that have a very, very high attention score because we want those instances to be classified as negative the next time. And this can be facilitated by using some pre-trained off-the-shelf CNN. In this case, it was a VGG16 without its last layer. It could also be some sort of ResNet to again get feature vectors of instances, just some embedding, then perform k-means to cluster those features, k1 to kn, and then randomly sample from these features to generate new bags. And these bags are all now hard negative. They all get the patient level or coarse grain level 0 and are then added back to the training data set. And by using this loop, which can be repeated as often as we want, we can sharply decrease the false positive rate, as you could see in the results. So we performed against some previous baseline or state-of-the-art method from 2019 and previous baseline methods with other pooling operators. But basically, we combined the attention and had negative mining or gated attention, which is another form of attention, which adds another non-linearity. To better solve the problem of false positives, which drops sharply, and get highly accurate classification of urothelial carcinoma in cytopathology, which was the first approach to do so. And if you analyze now our attention scores, we can see that with a high attention in both bags, we of course get our urothelial cells. So here are cancerous urothelial cells found in positive bags, and with relatively high attention in comparison, we also can find our urothelial cells in negative bags. However, in both bags, absolutely low amounts of attention are given to artifacts or cells that are absolutely not informative for the bag label. So, for example, squamous cells, which are large cells that are of no function, at least for cancer, or leukocytes, erythrocytes, bacteria. These are all attributed correctly with low attention. So much for cytopathology. And what I'm currently working on, which is the last project I'm trying to finish up before submitting my PhD thesis, is now multiple instance learning for the QCL-based, so again, infrared-based, labor-free spectral histopathology for the microsatellite status differentiation. So in colorectal carcinoma, so cancer of either the colon or the rectum, there is the problem of the microsatellite status. And basically, there are 3 different routes, and you can afterwards, as a patient, either be microsatellite stable or microsatellite unstable, which is MSI, which is mostly facilitated by some mismatch repair deficiency. And then you get some particular other formation of cells, which is called microsatellite unstable. And this microsatellite status is very, very hard for pathologists to observe under a microscope. So even if it now here seems as if there's a visual distinction, it's really, really hard to investigate normally. And normally to find out if a patient has now a microsatellite instability, you would need a specific gene-based panel. And this panel is A, very expensive, and B, it's not very common. So if you're a patient with suspected colorectal carcinoma, you will not often find out if you are now microsatellite stable or microsatellite unstable. But why is that important? It's a problem because the microsatellite unstable patients, they are being subjected or can be subjected to a specialized immunotherapy that greatly increases their chances of healing, of triumphing over the cancer disease. So we would like to find out easily from the tissue itself, without this gene-based panel, if a patient has an MSI or an MSS status, because normal pathology cannot do so as easily. So as I've said, we are based on now these hyperspectral images, so 2D images with spatial resolution, and in the third dimension we have now our spectra with 427 data points at each pixel, which makes the image even larger than these gigapixel whole-site images are in general. And to focus on some sort of sub area, we try to apply some tumor segmentation mask obtained by a different model, because this MSE and MSS status is mostly found in the tumor itself. It can also be found in the related areas at the outside, but we will focus on the tumor to just shrink down the size of tissue that we need. Then we tessellate or tile our image into patches, and then basically perform some sort of feature selection or compression again to work on spectral regions that interest us. Then perform multiple instance learning, tune that for a bit, and then basically get our results. So this is now a slide of tissue overlaid with the light blue area of tumor that is present in this tissue. And after analysis for MSE, MSS, we can then again assign attention scores for patches that are, for example, red, which are highly indicative for the MSI status, or green if they are not indicative for MSI status, and then vice versa, MSS, because both are mutually exclusive. However, the biggest problem in this setting now, so far it's generally easy and applicable. However, the big problem is here feature selection or feature compression, because these spectra are so large. So even with the multiple instance learning methodology and not based on CNN on the whole image, we cannot feasibly feed these images into our formulated setting, because they are just simply too large for the GPU memory. So what we need to do is we need some sort of spectral compression to find the informative regions in our spectra and to shrink down the images for a bit. And what we've mostly used are autoencoders, or basically pre-trained encoder compression. So based on unsupervised representation learning that we've previously published, we are based on the stacked contractive autoencoder that basically has all of the spectra as input and tries to reconstruct them, and is then trained layer by layer in a stacked greedy supervised fashion, unsupervised fashion. And that was used to relatively high success, as we can now break down the spectra from over 400 wave numbers down to, let's say, 16 wave numbers. What we've also tried is the minimum redundancy and maximum relevance algorithm, or MRMR, which selects the spectra or the wave number points, data points in our spectra that that basically keep the most amounts of variance, and as such reduce the number of redundant information and maximize the relevant information for us. And last but not least, what I'm currently trying is neural image compression, which is a quite interesting paper from the realm of computational pathology. So where the patches or the images are in M by N by 3, so RGB images, of course, and apply that to our spectral images. And in this case, we would have a patch embedding again. So each patch is broken down by an encoder into some vector, some embedding. And then we tile together the image again from these embeddings. So we get a compressed image that is now shrunken down in the spatial dimension. So M and N are squished and are smaller, but the depth is, of course, increased. And we are currently trying to use that for our spectral-based approach. Okay, so to get back to computational pathology on H&E-based images, I would like to introduce to you the very much, I would say, gold standard method at the moment, which is CLAM, or clustering constrained attention-based multiple instance learning. And again, as I've said, this is again a method for normal computational pathology. You could also use it for cytopathology, but it's mostly used for histopathology, so for pathology of tissue. So again, we have our patient whole slide images. We select some region. The region is segmented from the background. We exclude any holes, and then we tessellate the image into patches. And now what they did, what I think is the most interesting part of their work, is part B here at the bottom. So basically, they went and took out the part of feature extraction, and they basically shifted it from previously being in the model to leveraging it outside of the model and outside of the GPU. So they performed it basically not in parallel, but previously. They took all of their images and performed feature extraction down to some embedding vector. So it's not a square image, but an embedding vector by using a truncated ResNet, and then just saving these embedding vectors. And only then they perform the multiple instance learning with attention and so on, but only on these embeddings. So by basically doing the feature extraction previously, they save a lot of memory and can work on much larger images, as they do not need any convolutional architecture in the multiple instance learning approach. And also because the multiple instance framework can now have access to a much larger number of features, so they can work with larger images. And here in their attention backbone, they also extended it to a multi-class approach. So now, instead of only having a binary multiple instance formulation, they can have as many classes as they want, which can be useful for example, tumor subtyping, if we want to decide between multiple classes. And yeah, they also introduced something else, which is, I think, a bit similar to hard negative mining, as it better informs the decision of the on the back level, which is instance level clustering. So it basically uses the ground truth annotation, so the label for the patient bag in the clustering layer, and uses attention scores to basically generate pseudo labels for both the highly and the weakly attended patches. So here in red we have the highly attended patches with positive evidence, and in blue we have the negative evidence for lowly or very, very weakly attended patches, in order then to learn a separable patch level feature space that can be separated by a support vector machine. And this clustering loss is then added to the loss term in general. So it's used as an additional loss term for training. And they found that this is a very good approach. And after which, with the attention scores, they can again do attention pooling to some combined vector representation and then get their classification. And if you take a more fine-grained approach to these attention scores, you can generate these heat maps for interpretability. So here, this is clear cell renal cell carcinoma, so cancer of the kidneys, or of a specific part of the kidneys. And by having these fine-grained annotation maps with high attention in red and low attention in blue, we can even achieve some sort of segmentation, even though segmentation was never the task. So remember, we just trained on the issue of a patient level label for classification, and still the attention system here enables us to get some sort of fine-grained annotation and some sort of semantic segmentation that lets us see structural representations in the tissue, which is, I think, really, really interesting. So to get back to the where problem, so as I've introduced in the beginning, we had the what and the where problem. And with the multiple instance assumption, we really diminish the where problem, because we do not have any contextual or spatial awareness, as I've mentioned now multiple times. And that is, of course, a problem, because as I've said now in cytopathology, it's not the case because there's no spatial relationship, but in histopathology, so in regions of tissue, there it is, of course, a problem. Because if we have such a whole slide image where we have a lot of tumor detected regions in some sort of cluster, or maybe multiple clusters, then, of course, this is most likely a whole slide image with tumor. However, in images where we only have singular regions spread all across or scattered all across the image, this is most likely not a whole slide image with tumor. And finding this difference is quite important, but not possible for current multiple instance learning approaches, because they have no spatial awareness anymore. They are just working permutation variant. The number and ordering between the patches is completely irrelevant. And as such, we have quite a big where problem. And this was recently tackled by sparse-conv-mil by Le Rousseau, which is a sparse convolutional context-aware multiple instance learning for the whole slide image classification. And they try to sample as many regions as they can, or as many patches as they can, and not only embed the tiles into tile embeddings, as we do normally in multiple instance learning, but also save the selected locations for all of those tiles. And by having the locations, they can build a sparse map of basically a two-dimensional map where each position now carries the embedded tile with its specific location. But of course, due to the sampling strategy, there are, of course, large areas that do not have any data available at all to them. So they need a sparse convolutional setting. And by performing sparse global average pooling, they get a whole slide image embedding then afterwards, which can then be classified into probabilities for classes. And I think that this is one of the big next step forward. So to have some sort of system that integrates this locality, so the locality that would normally be inherent to CNNs, back into the multiple instance setting to better learn contextual features. Okay, so now we are nearing the end of my talk. And just as a brief outlook, I would like to tell you about the current interesting problems that we face in computational pathology, which are based on privacy and federated learning. So this is now from a paper from the same group that published the CLAM paper. And what is a big problem in computational pathology is that we are often based on working with very more or less artificial data sets. So they might be data sets from the clinic, but they are always highly curated. So they are from a single clinic, they have limited amount of patients, they have the same staining protocol, and so on and so forth. What we would like to do is to have or to integrate the information and data from many clinics. So to do a multi-centric study for example, across a whole country, across the whole globe, and so on. But this is not so easy because, of course, of data privacy laws. So transferring patches or even whole-slide images is very costly because of the associated privacy. It's often forbidden even by regulatory approval authorities. And yeah, transferring these images has a high cost just of transportation even and storage. So instead of collecting and integrating one data repository and training on that as we do normally, we would like to apply now federated learning, where we have not only one site, so one clinic where we do our approach, but instead we have multiple sites. And in this case, each of the data stays where it is. So it's silo federated learning, where all of our features extracted from those patches are left in the clinic. And also the model and one computer with maybe a GPU is left at the clinic. And each of those models computes one epoch itself, and then sends it back to some master server that does not have any contact to the data, but that can integrate all of the results, and then again give back the weights and update the models at the local sites, which can then progress with the next step. So this federated learning also enables differential privacy, and differential privacy means that we can now, by sending the weights, we can add some small perturbation from Gaussian random noise to our weights, to better be defended against some sort of malicious attacker that would like to maybe catch our data or influence our data in some sort. So here the global model is updated by averaging all the model weights received, maybe with some coefficient based on the number of data located at each location. And I think that this is a very important step, because while we have now many state-of-the-art approaches in computational pathology, and we are beating state-of-the-art currently, and new approaches and methods are coming out every day, we are still very, very far away from real application in the clinic. So, and that is mostly due to the regulatory requirements that needs us to keep data in the clinics itself. So we would like to capture the wide variances across multiple stations without integrating them in one repository. And I guess this will bring us a big step closer towards really getting computational pathology into clinics and into regulatory approval, which is at the moment one of the biggest challenges. And what I would like to do in my future, so for example in the postdoc that I do, is that we solve the scaling and efficiency problems of attention that we also encounter in federated learning, but also in non-federated learning. Which is that although the multiple instance learning attention that we are now currently using, and that CLAM is using, that all of the state-of-the-art approaches are using, is basically a simplified version of attention, as we are only having the weighted averaging of instances, as I've said. But what we would really like to have is the full self-attention that is used in transformers or vision transformers, which comes with positional awareness, because we want this spatial relationship between our patches. And so the question is, or the task is, if we can somehow model long-range interactions either without attention, or if we use attention without the prohibitive computational cost that makes it unscalable to large data sets. Or not to large data sets, but to large data in general in the form of gigapixel whole-slide images. And I think that possible solutions in the future will include most likely alternative frameworks. So for example, either better attention mechanisms, for example, linear attention, from the linformer, or even models that are neither CNN nor transformers, such as the NLP mixer model, which I think is really, really interesting, especially for the CLAM approach, as they did the feature extraction outside of the model anyway. So we can use the NLP mixer on the image embeddings and not work on the image itself, which I think would be quite interesting to get the positional awareness between the patches, as they could be encoded in the NLP mixer. And regarding an alternative framework, I think that lambda layers are currently really interesting, from Ivan Belle from last year's ICLR, lambda networks modeling long-range interactions without attention, because we can use these lambda layers instead of self-attention to capture interactions by transforming contexts into linear functions. So in an image, if we have some query, which is most likely a pixel, or in the MEL case, it would be one patch, to their local context, so to their specific region, and also in relationship to the global context, so the whole image. And instead of building the attention maps, which are really computationally not really inefficient, but really computationally expensive and memory extensive, we instead could propose to use lambdas, so fixed size linear functions that can model then both contextual and positional information, which would make it more memory and speed efficient. And integrating that with the multiple instance setting would give rise to lambda multiple instance learning, which I think is a very interesting next step that I would like to follow up with Dr. Anna Rolf, who is who was a long-term mentor of mine, who's now at the German Aerospace Center with expertise in this field. And I think that is a really interesting new direction. So to summarize at the end of my talk, so I think that multiple instance learning currently is the most prominent approach to weakly supervised learning, especially, of course, in computational pathology. It's absolutely the gold standard method. So please, if you want to work with that, check out CLAM. It has a great online implementation. Still, we have current challenges that we need to face and that are quite hard to solve. So we need some sort of spatial and contextual awareness to better integrate global information across our slide. We cannot just work on the patch level. I personally am interested in the application to high-dimensional spectroscopy, of course, because I'm coming from this field of Raman-based imaging or infrared-based imaging. And also, a next big step will be privacy-preserving federated learning to really get us closer to regulatory approval and to get these methods that are really interesting into real-life usage. And yeah, these are people that supported me in my PhD study. So my first and second supervisor and my long-time mentor. If you have any questions afterwards, you can write me a mail, find me on Twitter, or look at my code on GitHub. And with that, thank you very much for your attention. And I'm happy to take your questions.
Okay, thank you very much for a great talk. So now we're gonna move on to the Q&A section. So could you raise your hand if you have a question? Okay, so Lingu have a question. So could you speak?
Hello, I'm wondering, can you hear me?
Yeah, I can hear you.
Okay, thank you. Thank you very great for the very great talk. It's so interesting. So I just have one question. I'm particularly interested in the like the multispectral pathology part.
Mm-hmm.
Yeah. So I'm wondering, like, what is the spectral range for your for your image?
You mean physically?
Yeah, physically.
Like, yeah, it's 1,800 reciprocal centimeters to like 900 reciprocal centimeters.
Sorry, 1,100. Sorry.
1,800, so 1,800.
Well, 1,800 nanometer.
Not nanometer, reciprocal centimeter. So
yeah, I mean the spectral resolution.
Okay. Spectral resolution is like I think it's, so you mean visually? So
no. I just like, for example, you have seen this spectral. I just wondering, like, what is it only in visible range or also including the near infrared range?
So this is near infrared. This is only near infrared.
Oh, okay.
Yeah. For the Raman base, so this is infrared based. For Raman base, we would have visible to near ultraviolet.
Okay. Oh, that explains, because we have do a lot on the multispectral imaging. We find that in the visible range, it didn't provide any more particular information. So I'm just wondering how. But so as you can see that like in the near infrared range, that it can provide a lot of the more information in the net.
Yeah, especially for the biochemical states, because if you compare two spectra, so for example, let's say you have a spectra of a pixel that belongs to cancer and a spectra that belongs to a pixel that is healthy, from healthy tissue. They are vastly different, especially here on these top paths. So these are the amide1 and amide2 bands, which are particularly important for proteins, for proteins at that point. And in cancer, basically, you just have more proteins because they are much more highly active.
Yeah.
And that makes them easily distinguishable.
Okay. That's true. Okay. Yeah. Thank you. Yeah, I think it's very useful. Thank you.
Okay, thank you for your question. Any other question from audiences? Someone is raising hand. Okay, Takeuchi Sensei, could you speak?
Okay, thank you very much for a very nice talk. So yeah, I'm interested in your comment that the positional awareness would be very, very important.
Yeah.
Can I ask a question about in pathological images, like long-range interaction, the correlation between very distant area would be actually important for in the pathological images?
Maybe not between very distant areas, but at least between. So let's say in this image, right? So if we have here cancer, we would find cancer, let's say at this region here, right? So it would be important to have, let's say, at least a third of the image is highly related spatially to one another. Of course, it doesn't need to be distant relationship to like the other far part of the image.
I see.
So for example, here, so you often have clusters. A tumor is often a cluster in the tissue. So let's say this region, yeah. But of course, you do not need that much relationship from this pixel or from this position to like across the whole image. Maybe not that so much, but at least to more or less the local context.
Okay, thank you. So I have another question. So did you have an experience to talk with like a pathologist, medical doctor by showing your result? And I had the same experience, but it's the very difficult part is that when I saw this kind of results, the reliability is a very, very important issue. So the doctor gonna ask us like the attention. So I'm gonna say that this is an important part of the pathological image, but they want to know like how much they can believe that. So are there any idea that, do you have any idea that providing the reliability of the attention you found by MIL? If you have some idea, please share it with me.
Yeah, we found the same problem because so I'm not working, or we are not working in explainable AI, but you would need some sort of explainable AI to better formulate the decision that was reached and explain them back to pathologists and lastly to patients. And yeah, you're right, that is very, very hard. And especially in the beginning, when we founded the institute and we've worked on this data sets, we had problems to really get in contact with pathologists because they were of the impression that we want to basically substitute pathologists or substitute their medical expertise. And of course, we do not want to do that. We just want to provide clinical decision support systems to better, to enrich their decision, or maybe to use it in countries that do not have access to pathological expertise, for example. But you're right, reliability is a huge issue. So yeah, that's why I said, so for example, a study like that one. So a study like this one here. So we had really good results, of course, and we have like big area under curve, low false positive rate, and so on and so forth, but it's only for the patient, and it's only from a single clinic, because working on large data sets is so hard, right? So as I've said, in the end, working on federated learning systems with a large number of clinics that cooperate with you, where you can integrate large variances, I think that will lead to a much more reliable and robust system. That will be really important.
Thank you so much. Yeah, so yeah, I agree. Thank you so much.
Okay, so we have 5 more minutes. So if you have any question, please raise your hand. Muhammad Joni, could you keep on?
Yes. Hello.
Hi, Muhammad.
Hey, Yeshua, how are you?
Yeah, great.
Yeah, I heard about the talks. I was very interested in attending.
Okay.
I was thanks a lot for the nice talk. I'm just okay. There are so many interesting aspects. I'm just wondering about what do you mean by including spatial or contextual information in a neural network? Is it some kind of transformations that are applied before getting into the network?
Yeah, it's mostly some sort of positional embedding, right? So because you can see it here, for example. So here, I mean, this is on the level of cells. So here's not a problem, but these cells in a bag, this whole bag is shuffled around, and there's no relationship between the patches anymore, right? if we have tissue, it's very, very important where the patch stems from. So if it's a patch that is closely to the tumor or far away from the tumor, is very important to get a better analysis. And for example, in self-attention approaches such as transformers and vision transformers, they have this positional embedding because they are sequence-based information systems, right? And so they integrate this positional information, and we do not do that currently in multiple instance learning. It's not possible because the model is permutation invariant, and it must be permutation variant at the moment, right? And I think that is a drawback, and I think we need to solve that in the future.
I see. Yeah, because it's a similar problem to what I'm facing now. So I was just interested in knowing this is some kind of the same challenge.
Yeah.
Okay. Yeah. Thanks a lot.
Okay. Any other question? Okay. So let me ask at the same point about the positional awareness. So in the multiple instance learning, I understand that every patch is treated independently. Is that the reason why the position cannot be taken into consideration for the classification?
Yeah. I don't know if it's the reason, but at least it's the mode at which it's done currently. So multiple instance learning is like this really old principle from like 1997, which was originally for drug discovery, right? And that was really lacking to apply to images in the first place. And now it's only applicable to patch-based images for pathology due to the attention principle. And the attention principle already gives us some sort of like key instance analysis. But still, yeah, that's the reason, because the multiple instance assumption, at least in the case as it is currently used, is based on a permutation variant model. That means, yeah, we cannot have some sort of positional embedding at the moment, right?
Okay.
Or at least I'm not aware of any work that has successfully integrated this information yet.
Okay, so I am not really familiar with transformer, but is it very difficult to extend the positional encoding to the two-dimensional pictures?
Yeah, I don't know. So extending like transformer or vision transformers is very hard, because these are so they are even more memory hungry, as you might know, than normal CNNs already, yeah, right? Because of the attention map that they build, which is quadratic to the input. So for gigapixel images or even these patches, they will blow up in size that would fit on no GPU on the planet currently. So like the vision transformer is only working on ImageNet, and the ImageNet images are what, like 224 by 224 pixels or something, right? And integrating the positional embedding into multi-instance learning, I don't think that would be so hard. So that's why I proposed like the last slide, where I said, okay, maybe we could either have like the MLP mixer system, which is quite interesting, by working on the embeddings directly, which integrates positional awareness, or by using these lambda layers, which basically are a positional encoding and transform then the local context into those lambdas to form lambda mill. I think this is really interesting. Yeah.
I see. Okay. So resolving this point might be a very good future direction, right?
Yeah, absolutely. And this is the point that I've submitted now to the funding application I've told you about. Yeah.
I see.
Okay. Because I think it's a really interesting decision for all of those applications. It's based more in theory than in application, but yeah.
Okay, and let me ask another question. So could you show the slides about the negative instances, something?
Yeah. This one.
Yeah, so I couldn't understand. So I could understand how you extract the clusters, but I couldn't imagine how you can reflect the clusters to the training sets. The leftmost.
Yeah. So from the clusters, these are just now cluster features of all of the hard negative instances that we assume or that we found, right? And you can just use any random sampling strategy by picking, for example, uniformly, like picking one from 1, one from 2, one from 3, and so on, yeah, into a new bag or some other strategy. And then from all of these picked instances, or from the picked features, we relate back to the original patch image and then put it into the bag. And this does not have any label, right? Because it's artificial. We just synthesized it. And then we stick the negative label to it, and then just add it back to the training data set.
Oh, you give negative labels to these instances.
Exactly.
And
This, because we assume, so it was a positive back. We know that because it's our training back, right? We know it's negative, and we know that we have a false positive classification, right? So the model said positive, but we know it's negative. So we want to better understand information about patches that had a high attention in a false positive bag, and that is the method to do so. Yeah.
So does it actually suppresses the negative instances having higher attention values?
Yeah, it does, because in the next training step, the model now better learns information from these bags that are now again assigned as negative, and learns about those features, which also then suppresses those features in other bags that were previously misclassified as false positive. And if you then compare, like if you compare like training 1.1, then do hard negative mining, next training one, the false positive rate decreases more and more and more. Yeah.
I see.
So also on validation sets. Yeah.
Okay, so now 1 hour part. So if we have no question, I'd like to finish this seminar. No question anymore? Okay, so thank you, Dosha. Thank you for a great talk. So I would like to close the session.
Okay, thank you very much.
Thank you very much.